Hi everyone. In the last lecture we have studied all about the SR flip-flop. SR stands for set and reset. So in today's lecture we'll study about the JK flip-flop. It is the expansion of SR flip-flop. JK names come from the scientist name who actually developed this flip-flop. Okay. So in previously we have studied the SR flip-flop. SR flip-flop we have an invalid condition. So to overcome this invalid condition, the scientists developed new kind of flip-flop that is called JK flip-flop. And JK flip-flop is nothing but the expansion of SR flip-flop. Let us consider this is a flip-flop which is called SR flip-flop, and we'll have a clock input here. This is my S terminal, this is my R terminal, and the output is Qn, and other one is Qn complement. To develop JK flip-flop from SR flip-flop, what they did, they took two AND gate, one here and another one is here. The output of AND gate is fed to S and R. Okay, one of the input to the AND gate is J and the other one is K. The remaining two input to the AND gate will be the output of SR flip-flop. So this is Qn complement, and this Qn is again connected into the input of second AND gate. Okay, so this completes the JK flip-flop. That means by using SR flip-flop, we can by using SR flip-flop and two AND gate 1 and 2, we design the JK flip-flop. We'll start the truth table. That means when JK is 0 0, Q becomes Qn is equal to Qn. This is a table from SR flip-flop. Again from 0 and 1 we got 0. Then 1 0 we got 1. But in 1 and 1 for SR flip-flop we used to get invalid condition. But that is actually rectified here, and irrespective of getting invalid condition in JK flip-flop we are getting Qn complement. Okay, that means we can see here Qn is the previous state. Qn is the previous state and 0 is reset. 1 is set. Okay, and here Qn is previous state, here it is the complement of previous state. Okay, that means for example previous state is 0 and complement of previous state will be 1, or previous state may be 1 and complement of previous state is 0. It clear that whatever the previous state will be, here we'll get the opposite of that, the complement of that. That is why we can name it as toggle. Okay, by extending this truth table we are getting characteristic table. So let us design the characteristic table. Okay, characteristic take variable as J, K, Qn plus 1. That means two input, the present state and the next state, or previous state and the present state. Okay, so for each combination we may have two different Qn. Like for 0 and 0, Qn may be 0 or may be 1. So we'll get two combination, right? And from the truth table we have seen that for 0 and 0, the next state will be the previous state, right? That means the next state will be equal to the previous state. It is 0 here, it is 1 here. For 0 1, so we have two combination 0 and 1. Likewise we write 2 0 and 1. Okay, so from the truth table we see when J is 0, K is 1, the state will always reset. So irrespective of the value of previous state, the next state must be resetted. That means the next state must be 0. Again, for 1 and 0 combination, 1 and 0, so it will take two value 0 and 1. So from truth table we see when j is 0, when j is 1, k is 0, the next state will be set. That means next state will be 1. That means irrespective of the value of the previous state, the next state will be 1. Right? Again, for combination of 1, 1, we will have two combinations 0 and 1. From the truth table it is clear that when j and k are 1, 1, the next state will be the complement of the previous state. So here it is next state, here previous state. Previous state is 0 here, the complement of previous state is 1. Here previous state is 1, the complement of the previous state is 0. Okay. So this is nothing but my characteristics table. So if you take j, k and qn are the input variable, j, k and qn are the input variable. So you can see this table represents decimal 0, 1, 2, 3, 4, 5, 6, 7. That means to get, so from the characteristic table, it is very easy to design the characteristic equations. So this is 3 variable K map, go for 3 variable K map. Right? So from this K map, we'll get this is a pair and these two and create a separate pair here. So we can take these two pair also, no problem, but here we are not taking because all ones are covered. So from this truth table, from this K map, we can see qn plus 1 is equal to, so from this we can see j is not changing, and from these two column we can see qn complement is not changing, plus for this column k complement qn. So this is nothing but the characteristic equation for JK flip-flop. Okay, the excitation table, if we have qn and qn plus 1, so we have two variable, that means present state and the next state, and for these two variable we have 4 set of combinations 0 0, 0 1, 1 0 and 1 1. That means to get these 4 conditions, what should be my j and k? This is the meaning of excitation table, and this excitation table is actually used to convert one flip-flop from another flip-flop. Anyway, so this is 0 0. From the characteristic table, we can see 0 0 is present here and here. That means for these two rows, we can see j is 0 always, but k is changing from 0 to 1. So I can write j is 0, but k is invalid. That means for any value of k, if my j is 0, I always get qn is equal to 0 and qn plus 1 is equal to 0 also. Likewise, for qn 0 and qn plus 1 1, where to get? I am getting from this. So here and here also, these two row represent j is 1 and 1 always, but k is 0 and 1. So I can write j is 1, k is invalid again. That means for any combination of k, if my j is 1, I should get qn is equal to 0 and qn plus 1 is equal to 1. Right? So we are getting 1 0 combination from here and here. This is 1. Okay. So for these two row, we can see j is changing from 0 to 1, but k remain constant as 1. So I can write j is invalid and k is 1. For any value by j, if my k is 1, my qn and qn plus 1 takes the value as 1 and 0. For 1 and 1, and getting from here and from here, we can see j changing from 0 to 1, but k remain constant as 0. So J is invalid and K is 0. That means for any value of J, if K is 0, my Qn is equal to 1 and Qn plus 1 is equal to 1. Okay, so this is the excitation table. But we have a demerit in JK flip-flop. This is very important. I will create a separate video for this around condition. So we'll explain in the next lecture. Okay, so this is for JK flip-flop. So the to overcome this race around condition, we will design D flip-flop. Okay, that is delay flip-flop.